Yeah, I should add here the connection. This is displayed in video 26, video 26, and simulation with like C# is video 27, and now disturbance behavior starts video 28. Disturbance behavior. This is an interesting discussion because this fits more to the realistic behavior of a cruise control, because people want to use cruise control to have constant speed in spite of disturbances like strong wind, or the most important disturbance is driving up or down a hill. So I want to simulate now, discuss one special disturbance, simplified in the following way, simplified in the way that my car is reaching a hill at time 0, and then it has to drive up. That means now we have a gravity pulling down the car. That means there is a force back, or a negative force, which is added to the motor power. Yeah, so this could be understood as a negative addition for a constant motor power signal in our signal block diagram. I just make a copy of the signal block diagram with one difference. Now I have, as already done in my simulator, I have a second input with negative feedback. This is my PI controller. This is my PT1 process. And this is now a disturbance. Say power index Z, because Z is the typical letter for disturbance values. So we have speed, we have an input for our reference behavior, and now addition for the power signal for the disturbance. And I want to make a very concrete situation, calculate the response of this concrete simulation. Is I want to have a power signal which is negative because I'm driving up, so I subtract power from the motor power, so that the power which can accelerate and move the car is smaller. I want to have power signal which looks like this. It's again a step function. Yeah, step responses are very good to calculate. I want to have a step response with an amplitude of 20 kilowatt. A fictive negative power of 20 kilowatt is subtracted to this motor if I reach here this corner of the hill. Simplified. Of course, this is a bend, not a corner, but of course we assume that the force pulling back starts at once, like this step function. Has an amplitude 20 kilowatt. That means if I'm driving 100 kilometer per hour, let's assume what happens without controller. Without controller, what will the speed doing? We are here driving with 100 kilometer per hour. We know what do we need for power to get this on a horizontal part here. We need power. Go back to our measurement. 100 kilometer per hour. In our situation, needs 40 kilowatt motor power. So that means here the motor pulls my car with 100 kilometers, with 40 kilowatt. Now I subtract 20 kilowatt, and you can imagine what happens after some time, after many seconds. The speed goes down with exponential curve. 10 seconds is the time constant of the motor. The exponential curve goes down to half of the speed, because half of the speed is necessary to pull the car up the hill. So the speed goes down to 50 kilometers per hour without controller. And we want to analyze now what happens if our controller is active with our KC is 4 and our TN 10 seconds. What is the reaction of my speed in this situation if we have a controller? For this, we have to first talk about a little bit about zero initial conditions. Our transfer functions and all discussions we have done before assumes zero initial conditions. In this case, we have no zero initial condition because we want to analyze the situation if this is a constant value of 100 km per hour. What happens if we now add, in this situation, to a second input a signal to my loop? Then we have a reaction here which depends on this signal and depends on that signal. So we have a system with 2 inputs and 1 output, and the question is, how can we do this? The solution is to calculate the output V depending on W and PZ. We use the system property which is linear. Now we want to have linear PI, linear PT1, and then the system is linear, and the linearity then gives the possibility to work with one of the 2 main properties of linearity. The name is the Superposition Law. Superposition Law. Yeah, if your system is linear, then 2 principles are valid. It's first the superposition law, and second the principle of amplification. Here the superposition law is good, so we can calculate the output of this system V as a sum of the input power disturbance, if this is 0, plus input of this, if this is 0. So we can calculate 2 different reactions. The one reaction is a disturbance reaction, and the other reaction is a reference reaction separately, and then add the results, and then we get a total good curve. So in the table I will show you what I mean. I need in this situation first PZ is 0, W is 100 km per hour constant. Then I know because there is no change in my desired value, I know with my PI controller there is no control error, as we have discussed before, that the output speed is also constant, 100 km per hour. Now in the second step, we set the desired value to 0 and assume that PZ is my step function, then V is step response, and total result is the addition. both signals. Yeah. So the first step is okay. Second step we have to do with our mathematical methods. What we need is the step response. If our input PZ is a step function, this is 0, because we are here in this section. This is input, this is output, this is 0. That means we have the following signal block diagram. Now, new SPD, I make a redesign, a redrawing of my signal block diagram so that PZ is my input. PZ is input. Then the process function follows. K process, T process, V output follows, and then you see the process output then is connected via the PI controller with this negative sign. With PI controller to the input. The minus sign here, I will do this. The minus sign here, input 0, the plus sign here, we'll discuss later. You see this minus sign? It's just an inverter in this line, but it is unimportant if this inverter is at this position. A summing point with 0 input can be removed, and the minus sign can be shifted to that position so that we have a negative feedback. And the transfer function, you can say the disturbance transfer function, is that function where output speed is related to input disturbance power of P. So, and with our signal block diagram reduction methods, we can just write down my transfer function as 1, minus sign, but here's a plus sign, so we need a minus sign here, but we have in the feedback loop an inverter, so in total we have a plus sign here. This is again F process, F controller. Here we have again the same denominator, F process, F controller, but in the numerator now we have FP, the process transfer function, because this is the connection between our actual input to our actual output. Okay, so we replace now with our given single transfer functions. This is the process, K divided by 1 plus PT. And in the denominator we have the old well-known product of the controller transfer function multiplied with the process transfer function with the well-known pole compensation erase of those quantities. If we now factor this out, we have to multiply with Ptn, with this denominator, and the complete numerator denominator multiply with this denominator. Then we get the following final expression. This is K, the numerator, times this is erased, but times this is just has to be written here. This one has to be multiplied with this denominator and this denominator, so we have a 1 plus Pt multiplied with Ptn plus, and this KCK is the numerator of the denominator. Ptn is reduced, but 1 plus Pt is still a factor we have to write here, 1 plus Pt. And you see, okay, this is now a second order function in the denominator. We have a p times p, p squared. We have a first time expression, p, and here a p, and we have p to the power of 0 constant factor in the denominator. If I order this in a new way, then we can again write p times k times tn, and here I factor this out. This is kck as the factor without a p, kck times 1 plus p times what? P times tn coming from this position, and times t times kck plus t times kck, and finally plus p squared t times tn. So this is a second order function. If we look into my workbook, then you see there is a row 8 called dt2, which carries a p and a factor k in the numerator, and a second order function 1 plus anything p times anything p squared in the denominator. So exactly we can find out that the resulting disturbance transfer function is a dt2, which is not discussed yet. So we just can look into the workbook, page 16, if you can put some equations, or I show you. I want to go not too deep into detail for discussion with numerical values, but you see I can normalize this function and use all these parameters which are known. Yeah, k is the process k with 2.4, kc is the selected k with the value 4, tn is 10 seconds, this is 10 seconds. So all values are given, so the transfer function is known, and we can discuss it and later also simulate it. What we can see is that the dt2 has the following step response. dt2 step response from workbook, page 16, row 8. Row 8 is, yeah, the step response has a maximum and goes back to 0. This curve can be copied. We can say, okay, step response has the important behavior. Step response dt2 is just increase, maximum, decrease, final value 0. So that we can say, okay, with this knowledge, we can put now this together. Furthermore, we have a negative input, so our step response is inverted. We have to add to the output a constant value of 100 km per hour, so that we can say in total the response of our speed looks like this. T speed, we have here a 100 km per hour starting value, and then we have to add this curve but with a negative sign, so a speed decrease will then the consequence, and then finally we'll see the original speed then is come back. So this is exactly that what the disturbance step response shows, that the speed in the first moment goes a little bit down, and then finally the controller pulls up the original speed to the desired value 100 km per hour. if this is acceptable or not depends on this value, delta V, and depends on the time behavior. So what I can give you is this T max T min value. We can calculate this. Now this is T max in our case. Now if we have an indicator for after how many seconds, minutes, hours the minimum point is reached, and then we can guess that the original speed comes back say 5 to 10 Tmax later. So it could be a good idea to calculate delta V and Tmax with workbook pages. I have to look where these are. Stop. Workbook page 18 plus 19. You can find details to DT2 block. For this you have make a coefficient comparison, our function with a given function. Then you can calculate for the step response the delta V and the Tmax value, and I give you now the resulting values. After some hours calculation, some minutes calculation, we can find that delta V is 3.87 kilometers per hour and Tmax is 2.56 seconds. So with these values, with our K4, we see, okay, the speed is 100 kilometer up to the corner of the hill, then this goes down to say 96 kilometers per hour, and then after 3-4 seconds this goes up back again to 100 kilometers per hour. And the question is this 4% change really a problem for your driver? Then of course you have to do something. If not, your disturbance behavior is absolutely acceptable, because this controller really pulls back the speed independent of the disturbance back to the desired value. There are no control error, we can say. No control error means the disturbance, the controlled value is exactly after some time equal to the desired value. Let's finish this with a simulation to show you exactly this curve, but without the shifting of 100 km per hour. I think this can be done by hand. I go back into the simulation program and we add now a step function to the disturbance input. This is a signal block diagram. Note the disturbance input here is 72. Disturbance input here is the desired value is 71. What we can calculate now is very simple. Now I have to check the speed, the gain of the controller. With the right mouse click I can reopen the parameter box of each block. You see I've switched back to 4. This is our situation. I should throw away my second PT1 block because I want to go back to our simple model. So I can delete this block, add a branch between this gap, and say OK, calculation of step response now with input number 2072, input step amplitude. Don't forget this is here, the minus sign is not written here, so I have the minus sign add to my amplitude here. I now calculate with a 20 kilowatt disturbance input and delete all curves. Want to see speed and delete this curve and calculate the disturbance value. And here you see from the starting point 100 km per hour, this goes down with nearly 4 km per hour, and then this was pulled up after 10 seconds. I have have 2% change, and yeah, if I go up to 50 seconds, you see, yeah, after here, this is 1% change, after 17 seconds, 1%, and so on. So this simulation fits to my calculation. We have to check the power signal. If you go up to the power, you see the motor power has no peak, just must increase its starting value up to 20 kilowatts. Yeah, that's to compensate the disturbance force, the disturbance power. Yeah? So there is no motor limitation, no limitation can influence our response in a negative way. What we can do, last step is we store this curve and check what happens if we increase now our controller gain to 40. What happens with my disturbance behavior? And you will see the disturbance behavior is much better. So the decrease is only now 0.5%. So I think this feeling, this curve gives a feeling there is no influence. The driver cannot feel if he drives 100 kilometers or 99.5 kilometers per hour. He feels the speed is held constant. That is what he expects from a good cruise control system. Yeah, so far this is the first project. You see what is missing is second order functions. What I want to do is the next step in the next video. We want to discuss not only a PI controller, we want to look on a more complex controller, which is also well known in many industrial applications. This is a PID controller. But this comes with the next video.